Hello, my name is Paula Tretkoff and I am Professor in the Department of Mathematics at Texas A&M University. This is a video abstract of my paper to appear in the Journal of Number Theory and entitled Transcendence and Complex Multiplication on Borcea-Voisin towers of Calabi-Yau manifolds. Elliptic curves with complex multiplication, and more generally Calabi-Yau varieties with complex multiplication, are of interest to a number of areas of mathematics, in particular number theory, and to several areas of theoretical physics. In this paper, I study a criterion for Calabi-Yau varieties to have complex multiplication, which has its origins in transcendental number theory. Let me go back and explain the situation for elliptic curves and the link with transcendental number theory. So we consider a lattice in the complex numbers, which is nothing more than a z-module of rank 2 generated by 1 and a complex number tau, which is not real. If we consider, instead of the z-module, the vector space generated over the rational numbers q by 1 and tau, then as it's a vector space over the rational numbers, every rational number acts on this vector space by multiplication and leaves the vector space fixed. However, it can happen that this vector space admits multiplications by numbers which are not rational. So these are non-trivial multiplications. And it's not hard to see that in that case, this number tau is forced to be imaginary quadratic. In other words, it generates a field of degree 2 over the rational numbers, or if you prefer, it satisfies a polynomial equation of degree 2 with coefficients rational numbers. We then say that the lattice has complex multiplication because it has multiplications by complex numbers, not just rational numbers. And instead of saying complex multiplication each time, we abbreviate that by the letter CM. Now, if we consider the equivalence class of complex numbers modulo translations by the lattice generated by 1 and tau, we get what we call a one-dimensional complex torus, which is often called an elliptic curve because it actually has a realization as the points on a plane cubic curve plus an extra point. So we say in that case that the elliptic curve has complex multiplication. Now, we've already seen that a lattice has complex multiplication if and only if this number tau is imaginary quadratic, so it's in particular an algebraic number, but an algebraic number of a very special type. One can also show that if the lattice has complex multiplication, then we can choose a model of this curve, or if you like, that this elliptic curve is isomorphic to 1, such that the coefficients of this cubic are algebraic numbers. So we say that the elliptic curve is defined over a number field. A rather deep result of Theodor Schneider, using techniques from transcendental number theory, showed the converse of this result. Namely, if I start with an elliptic curve defined over a number field, so defined by a cubic curve with coefficients, algebraic numbers, and if I know that tau is also an algebraic number, then the elliptic curve is forced to have complex multiplication. So at the outset, I make no other assumption on tau other than it being algebraic. And then if this cubic equation has coefficients in algebraic numbers, this much stronger restriction is forced on tau, that it be imaginary quadratic. Okay, so the lattice has extra endomorphisms, and so we think of the elliptic curve as having extra endomorphisms. In fact, has the maximal number in a sense that can be made precise. So one can make sense of this problem also for higher dimensional complex tori. And in fact, I proved jointly with Hironori Shiga and Jürgen Wolfart in the mid-90s an analog of this result of Schneider for higher dimensional complex tori, which have the structure of projective varieties. But another direction one can go in for generalizing elliptic curves is to look at Calabi-Yau manifolds Now, an elliptic curve essentially has one holomorphic differential form. In the expression of elliptic curve as a curve, it's dx over y, and it basically corresponds to the differential form dz on the complex numbers. And there are several definitions of Calabi-Yau manifolds, but they all contain the condition that this is a complex manifold of dimension n, which has up to a constant, a unique, non-vanishing holomorphic n form. So if you like, the higher dimensional analog of our dz. Now one can make sense of what it means for a Calabi-Yau variety to have complex multiplication, but I'm not even going to attempt to explain because it's too technical for video abstract. And one can also associate to a Calabi-Yau variety and its higher forms an analog of the number tau. It's called a period matrix. And so one can ask that if we have a Calabi-Yau manifold which has the structure of an algebraic variety, and if we know that the polynomials that define that variety all had their coefficients algebraic numbers, just like we did here for the elliptic curve, and if that matrix tau has algebraic entries, does that force the Calabi-Yau manifold to have complex multiplication in a sense that we can make sense of? And it turns out that we can actually prove this for a number of families of Calabi-Yau manifolds, and they had their origin in work of Borcea and Voisin, and also of Vivek and Zwo, and they're very well explained in a book published by Rhoda in 2009. That we're essentially able to generalize this theorem of Schneider, which gives a transcendence criterion for an elliptic curve to have complex multiplication, to the context of Calabi-Yau varieties in this case. Now, because this is rather a new field in transcendental number theory, we do give all the necessary background, and the examples are very explicit. So if you want to learn more about it, please read my paper. Just a final remark before I go. I said transcendental number theory, and that may not be clear why this has anything to do with transcendental number theory. And what's that? Well, a transcendental number is a complex number which is not algebraic, and the techniques used by Schneider and used by myself, Wolfert, and Shiga, and used in this paper that this is the video abstract of, use techniques from transcendental number theory, which is a theory of numbers designed to decide whether numbers are transcendental or not in a rigorous fashion. And so, for example, going back to the resultant elliptic curves, if we know that this number tau is algebraic and the curve does not have complex multiplication, then the coefficients of its defining equation have to be transcendental. So there's a way of formulating these results in a way that involves transcendental numbers. So, but much more importantly, the techniques of proof come from the theory of transcendental numbers. Thank you.